Yesterday, we learned a whole lot of information about the 4 quantum numbers. Today, we're going to take that information and actually assign the quantum numbers to each electron in some very specific atoms. Now, yesterday, I mentioned that the quantum numbers are similar to an address. And I mentioned that the principal quantum number was like the city that you're in. I mentioned that the azimuthal quantum number was like your street address, the number in the street. I said your magnetic quantum number was like your apartment number. And then I said the magnetic spin quantum number was like which bedroom you're in. Are you in the front bedroom or are you in the back bedroom? And analogies almost always break down someplace. And so while a lot of us share bedrooms with people, you know, husbands and wives usually share bedrooms and siblings often share bedrooms. In atom world, electrons never share bedrooms. Okay, so I just wanted to tell you that that's where the analogy breaks down a little bit, because electrons don't share bedrooms. They can't share any 2 quantum numbers at all. And so that's where the Pauli exclusion principle comes in. Pauli exclusion principle says that no 2 electrons in an atom can have the same 4 quantum numbers, which means they're not going to be able to share a bedroom. Okay, so the other thing that we need to understand as we are starting to fill these orbitals with electrons is that we're always going to start with the lowest energy level first. We had been talking previously about exciting electrons and allowing them to fall from one orbital down to the next orbital, but that's not what we're talking about now. Now we're just talking about where are these electrons going as we're filling the orbitals with them for each particular atom. So best way for me to explain this is just to do a couple of examples for you. We're going to start with a nitrogen atom, which I do think is one of the examples that he does. So whenever you're assigning quantum numbers, you need to start with an electron configuration, which is why I had you review that a couple of days ago. So the electron configuration for a nitrogen atom is 1s2, 2s2, 2p, forgot my 3 up there, 2p3. The atomic number for nitrogen is a 7, so that means in a neutral atom there should be 7 electrons. And if I look at my exponents up here, I've got 3 plus 2 plus 2, which does make 7. So I've got 7 electrons that I need to put into orbitals so that I can assign quantum numbers to them. Okay, so I am going to start with the 1s energy level and the s orbital. So if n is equal to 1, you're going to want to keep in mind over here, keep in mind these rules for quantum numbers that we've already talked about, okay? If n is equal to 1, the only possibility for L is going to be 0. It can't be anything else because it can't be any greater than n minus 1. If L equals 0, then the only thing that m sub L can be is also 0, because I can't have a negative or a positive 0. So this is also going to be 0. And then by convention, when I assign the spin number, I usually assign the positive 1/2 before I assign the negative 1/2, okay? So there's my first electron that goes in. My second electron that goes in is also going to have an n equal to 1, an L equal to 0, an m sub L equal to 0, and this is going to have a spin number of a negative 1/2. And if you recall from your first year chemistry course, we said that you can put 2 electrons into each orbital, so that's going to be the case here. So this right here is my 1s orbital, 1s2, 2 electrons, okay? Now we need to move up to the second energy level. So the second energy level, I'm going to have n equals 2. Again, I'm going to start with the s orbital, and so at n equals 2, I'm going to start with L equals 0, because that's the lowest possible number that it can be. If L is equal to 0, then m sub L is also going to have to be equal to 0, and we always start with a positive 1/2. Then when I go back through and I can add the next electron, I'm going to use the same 3 quantum numbers here, but now I'm going to put in a negative 1/2, okay? So these 2 electrons are the ones that go in the 2s orbital, okay? 2s orbital, so 1s2, 2s2. So I've got these two guys taken care of. Now I've got my two p orbitals. So I'm still at my second energy level, but if we recall, the p orbital has an L value of 1, okay? At L is equal to 1, I have 3 possibilities for M sub L. I can have a positive 1, I can have a 0, and I can have a negative 1. And so where do I start putting these electrons in? I mean, I have quite a few possibilities here. I only have 3 to go, so can I put 2 in the plus 1? Do I have to separate them out? How does all that work? Well, this is where Hund's rule comes in. Hund's rule says that for a given value of L, all the values of M sub L have to have 1 electron before any of them gets a second electron. I like to think of this like I call it the school bus seat rule. Now, I realize that probably the vast majority of you have never ridden a school bus. I rode a school bus when I was a kid, and maybe you've ridden a bus at some point in your life. What happens on a school bus tends to be, and probably other buses too, if you've got these big, long bench type seats, you get into the school bus and the early kids on the school bus always get their own seat because everybody goes to sit in an empty seat and they don't tend to share a seat with somebody else. It's only when every seat is full that then the next kid that gets on the bus has to share with somebody. And so it's the same way with electrons. If you have, remember we have 3 p orbitals, we have one along the x-axis, we have one along the y-axis, and we have one along the z-axis. Each one of those p orbitals has to have 1 electron in it before any of them will take a second electron, just like school bus seat. Okay, so that means I have 3 electrons left that I need to fill, or that I need to put someplace. And so that means one of them is going to go where M sub L equals 1, one goes where M sub L equals 0, and one goes where M sub L equals -1. Px, py, pz. And again, by convention, I always assign the positive 1/2 spin number first. Okay, so these are my 3 2p electrons, and I now have 1, 2, 3, 4, 5, 6, 7 electrons, which is what I should have. Okay, so what happens if I have a few more? So let's look at another example here. We're going to look at bromine, which again I think is an example that he does in the book. And bromine has a whole bunch of electrons, but thankfully he only asks us to assign quantum numbers to the valence electrons. So the valence electrons means it's the ones with the highest value of n. Okay, so I'm not going to erase quite all of this. So if I have a bromine atom, the complete electron configuration for a bromine atom is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5, okay? The highest value of n that I have in any of these is 4. And so what that means is that my valence electrons are the ones that go in the n equals 4 level. Now you may be looking at this going, wait a minute, how come I didn't finish the 3rd energy level first? Okay, this is one of those places where things get a little dicey, simply because with the way that you learned this, you've actually learned the difference in energy. The 3d orbitals actually have a slightly higher energy than the 4s, and so we tend to fill the 4s before we fill the 3d. However, when we're talking about valence electrons, we're always looking at the last energy level, and those are the electrons that are typically gained and lost first, or shared when an atom goes to make a bond. There are some exceptions to this, but like I said, it gets a little messy. We're not going to worry about a lot of those exceptions right now. We're going to stick to the more general rules for all of this. So basically just look at it and say, okay, if I'm asked for valence electrons, I'm going to look for the highest value of n. So let's adjust our chart here so we can fill these guys in. Without having to completely rewrite everything. Okay, so if we start over with that now. So basically what I have to do is I'm going to fill my 4s2 and my 4p5. So if I'm assigning electrons to my 4s orbitals, n is going to be equal to 4. You will remember that s orbitals have an L value of 0. And so m sub L is also going to be equal to 0 because of my rule over here. And so whenever I fill these, by convention, I put in a positive 1/2 spin first because the s orbital can take 2 electrons. My next electron that goes in is also going to have an n equals 4, an L equals 0, an m sub L of 0, but now my m sub 1/2, or my m sub s is going to have a negative 1/2 to it, okay? So there's my 4s orbital. Now I'm going to my 4p orbital. So what I do down here is going to be 4p. So once again, n is going to be equal to 4, but as you recall, the p orbital is when L is equal to 1. I've already used the 0. The p orbitals are L equals 1. When L equals 1, I can start with positive 1 or 0 or negative 1. By convention, we usually start with the positive numbers. And Hund's rule, the school bus seat rule, says that each one of these orientations of the p orbital has to have 1 electron before I can add 1 to another one. So all of these guys are going to have a positive 1/2. And this looks almost exactly the same as what I had in the nitrogen atom. The only difference here is the n, because I'm at 4 in place of at 1. But now I've got 2 more p electrons that I have to add. Okay, so I should have filled these guys in here. I've got 2 more electrons that I have to add. And so because each orientation of my p orbital has 1 electron, now I'm going to go in and start filling the second one. Okay, again, by convention, I usually start with the most positive value of m sub L. So my next electron is going to have an n equal to 4, an L equal to 1, an m sub L equal to positive 1, and now my spin is a negative 1/2. And then my 5th electron is going to be n equal 4, L equal 1, m sub L equals 0, and now this is going to be a negative 1/2. Okay, so these are the p's. So 4 s's and 5 4p's. Okay. Couple of other notes. One is that he does give you several what's wrong with these quantum number problems. 2 things that you generally want to look for when you're working those types of problems. First of all, make sure that all of the sets of quantum numbers are different, because you can't have any 4 sets. You can't have any sets of quantum numbers that are the same if you're talking about the same atom. So if you're talking about 1 atom and you have 2 sets of quantum numbers that are the same, that's going to be the first problem that you'll find with it. The other thing that he generally is going to do if he says what's wrong with the set of quantum numbers is something in this set of rules has not been obeyed. So he may say n equals 3 and L equals 3. Well, that can't be the case because your L can't be any bigger than n minus 1. Or he may say, well, L equals 1, but m sub L equals 2. Well, that's not possible. This has to follow this rule here. So check to see which rule has been broken when you're trying to determine if those quantum numbers are acceptable or not. Finally, he talks about degenerate orbitals being as identical energy levels. And if you recall, when we first started talking about quantum numbers, what I told you was that only quantum number n and the quantum number L affect the energy of the electron. And so because n and L affect the energy, the n and the L have to be the same if the orbitals are going to be degenerate. So for example, in what we talked about up here, the n and the L were all the same in these 4 p orbitals. So all 3 of these p orbitals are degenerate. Okay. Here, if I look at my 4s and compare it to my 4p, while the n is the same, the l's are not the same. So a 4s and a 4p are not degenerate orbitals. They're only degenerate orbitals if the n is the same and the l is the same. So all 4p orbitals would be degenerate, all 3d orbitals would be degenerate, but you can't mix the type of orbital along with the energy level. Okay, so that's degenerate orbitals. So you are going to get a lot of chances to practice now your ability to assign quantum numbers to electrons.